Hey everyone, I hope you're doing well today. In this video, I'm going to be going over some practice problems using the law of sines and the law of cosines. As you may already know, our Pythagorean theorem and our SOHCAHTOA are limited to right triangles. To help us solve non-right triangles or oblique triangles, we use the law of cosines and the law of sines to do so. Here are the three different formulas you can use for the law of cosines, as well as the law of sines. If you're curious where these formulas come from, feel free to check out my previous video where I go over the proofs. You'll know you need to use the law of cosines when you're given consecutive side angle sides of a triangle, as well as all three sides of a triangle. And you'll know when to use the law of sines when you're given the angle side, an angle side angle, or a side side angle. And just be careful of this last one where you might have the ambiguous case. And while I don't think it's against the law to not like this video, I really would appreciate it if you didn't not like this video. I'm pretty sure two negatives make a positive, right? Anyway, if you could like the video, I'd really appreciate it. Alright, anyway, let's get into some practice problems. Grab some paper, something to write with, and let's do some math together. Let's look at our first law of sines practice problem. In triangle ABC, we know angle B is 21 degrees, angle C is 46 degrees, and side C is 9 centimeters long. We need to solve this triangle. First of all, to solve this triangle, that just means that we have to find out all three angles and all three side lengths. We know that angle B is 21 degrees, so we can fill that in right away. We know angle C is 46 degrees, so we'll put that right over here. And we know that side C is going to be 9 centimeters long. And while we have these three bits of information, we still have to find angle A, and side B. At this point, I would recommend that you draw a triangle so that you can clearly see where all the sides and angles are. I went ahead and made angle B the smallest angle measure and C a little bit bigger, and side C is going to be opposite of angle C. Since we're given a side angle and an angle, we know we have angle side, so we're going to use the law of sines as opposed to using the law of cosine. However, before we do that, let's see if we can figure out any more information before we use any of the fancy formulas. Since we know two of the angles in a triangle and all three angles have to add up to 180 degrees, we can write an equation as angle A plus B plus C is equal to 180 degrees, substitute in the angles we know, combine them, and subtract 67 degrees from both sides to find out that angle A is equal to 113 degrees. I'm going to write that right in here, and I can put that in our answer. Now we just have two things to find out, the length of side A and the length of side B. Here's our law of sines where we have the ratio of each side length over the sine of the angle measure that corresponds with it. Since we know some of the values for sides A, B, and C and some of the angle measures, let's substitute those in. After substituting in, it's important that it still lines up that our unknowns here are side A and side B. And to be successful in this problem, it's really important to know that out of the three ratios that we have here, the only one that has complete information on the top and bottom is this 9 over sine of 46 degrees. This ratio here is the key to solving this triangle. Now let's write a proportion using the ratio that we do know and setting it equal to one of the ratios where we have a missing piece of information. And after that, we can write another proportion setting our known ratio equal to the other ratio that has another unknown. For the proportion on the left, we can use cross multiplication and rewrite it as b times sine of 46 degrees is equal to 9 times sine of 21 degrees. Dividing both sides by sine of 46 degrees, we can write b is equal to 9 times sine of 21 degrees over sine of 46 degrees. And plugging this into a calculator, we get that b is approximately equal to 4.48. And I'm going to write that right over here as well. And for the proportion on the right, we can also cross multiply and we'll get a times sine of 46 degrees is equal to 9 times sine of 113 degrees. Dividing both sides by sine of 46 degrees, we can say that a is equal to 9 times sine of 113 degrees over sine of 46 degrees. And plugging this into a calculator, we get that a is approximately equal to 11.52. And I'm going to write that right over here. And now we've solved this triangle. Keep in mind that when you're solving these triangles, you need a total of 6 pieces of information. In this particular problem, we were actually given 3 of them to start, and we could use simple algebra to subtract 2 of the angles from 180 degrees to find out the last angle. At that point, we had 4 out of the 6 pieces of information, and we needed to use the law of sines to find the last side of A and B. Using the law of sines, you can write proportions and cross multiply to get normal equations. After substituting values into the law of sines, you can create proportions, use cross multiplication, and then solve the equations for the missing pieces. Here's another practice problem using the law of sines. In triangle ABC, angle A is 22 degrees, angle C is 13 degrees, and side C is equal to 9. Solve the triangle. Let's start by sketching a triangle. Here's my drawing, and I made sure that angle C was smaller than angle A. Again, we have an angle, and a side. And to solve the triangle, we need these 6 pieces of information. We're given that angle A is 22 degrees, so we can write that here. And we're given that angle C is 13 degrees, so we can write that over here. And on top of that, we know that side C has a length of 9. Notice that we're given 2 angles, so we can actually figure out the third angle pretty easily. Angle A, B, and C should add up to 180 degrees. And we already know angle A and angle C, so we can substitute those values in. Combining the 22 degrees and 13 degrees, that's 35 degrees. And subtracting 35 degrees from both sides, we know that angle B is equal to 145 degrees, and we can write that right down here. Now that we have 4 out of the 6 things we need, let's just find the side length A and the side length B. Right here we have the law of sines, and we can substitute 4 out of the 6 pieces of information that we already know. After substituting in, notice how our 2 unknowns are still side A and side B. Out of these 3 ratios, the one that's going to be useful to us for solving for the unknowns is this 9 over sine of 13 degrees, since we know the top and the bottom. Let's take that ratio and write 2 separate proportions. First, we can write 9 over sine of 13 degrees is equal to b over sine of 145 degrees. Then we can write that 9 over sine of 13 degrees is equal to a over sine of 22 degrees. Just like the last example, since we have 3 out of the 4 bits of information, we can use cross multiplication to solve for the unknown. For the proportion on the left, we can use cross multiplication and rewrite it as b times sine of 13 degrees is equal to 9 times sine of 145 degrees. Then by dividing both sides by sine of 13 degrees, we can get this equation right here. And substituting this into a calculator, we get that b is approximately equal to 22.9. And I'm going to write that right over here. For the proportion on the right, after cross multiplying, we're going to get a times sine of 13 degrees is equal to 9 times sine of 22 degrees. Then if we divide both sides by sine of 13 degrees, we'll get this equation right here. And plugging this into a calculator, we'll find that a is approximately equal to 15, which is our last bit of information that we needed to find. Hopefully after the first example, this one made a little bit more sense. Let's try another law of sines practice problem. In triangle ABC, angle C is 63 degrees, side B is 9, and side C is equal to 12. Solve the triangle. Once again, let's start by drawing a triangle so we see what we're working with. Here's a sketch of a triangle with the given information labeled. Whenever given a side, and angle, remember to consider the ambiguous case where you could have 0 triangles, 1 triangle, or 2 triangles. Before we start trying to solve for the 6 pieces of information, let's first see if we're going to have 0, 1, or 2 triangles. To do that, you're just going to use your good old SOHCAHTOA. Draw an altitude or the height of the triangle, which I labeled h here. Because drawing the height or the altitude creates a right triangle, we can use our good old SOHCAHTOA and write sine of 63 degrees is equal to h over 9. Multiplying both sides by 9, we can say that h, or the height, is equal to 9 times sine of 63 degrees. Plugging that into a calculator, we find out that our height is approximately equal to 8.02. Since our height of 8.02 is less than the adjacent side to the angle of 9, we definitely can draw one triangle. But the fact that the opposite side of 63 degrees, which is 12, is greater than the adjacent side of 9 also confirms that. And just so you're aware, if the side that's labeled 12 was shorter than 9, we would have an ambiguous case and have 2 possible triangles. While it still might be a little bit confusing now, stick with it and it'll get a little bit more clear as you keep practicing. Because we have the information of a side, and angle, we're going to use the law of sines, and here are all the values that we know substituted in so far. Since we know that side B is 9, we can write that over here. And we know angle C is 63 degrees, and we can write that as well. In addition, we know that side C is equal to 12. Because this is the only ratio that we have the top and the bottom, we're going to use this to help us find more information. And when deciding the other ratio to use to form a proportion, don't use this one that's a over sine of a, since we don't know either value on the top and the bottom. It's not useful. So let's go ahead and write the proportion. 12 over sine of 63 degrees is equal to 9 over sine of angle B. Using cross multiplication, we can rewrite our proportion as 9 times sine of 63 degrees is equal to 12 times sine of angle B. Dividing both sides by 12, we can write sine of angle B is equal to 9 times sine of 63 degrees over 12. Because we know what sine of B is equal to, we can actually take arcsine of that whole expression to find out what angle B is equal to. Plugging this into a calculator, we can find out that angle B is equal to 41.9 degrees. Remember that the sine function and the inverse sine function cancel each other out, so whenever you're looking for an angle measure, you can take the inverse trig function to do so. Now that we have angle B, we can write it in right over here as 41.9 degrees. And now that we have two of the angles, we can add them together to get 104.9 degrees. And subtracting that from 180 degrees, we know that angle A has to be 75.1 degrees. Now that we have 5 out of the 6 pieces of information, let's find the last part, which is side A. Now that we found out that angle A is equal to 75.1 degrees, we can substitute that in to solve for side A. Let's write a new proportion. Let's write 12 over sine of 63 degrees is equal to A over sine of 75.1 degrees. Using cross multiplication, we can write A times sine of 63 degrees is equal to 12 times sine of 75.1 degrees. Dividing both sides by sine of 63, we can write A is equal to 12 times sine of 75.1 degrees over sine of 63 degrees. Plugging this into a calculator, we find out that side A is approximately equal to 13.02, which we can write over here. Just make sure you're being careful when you're given the information of a side, and angle. These key pieces of information will help you determine if you have 0, 1, or 2 triangles. Afterwards, you can just use the law of sines a couple times to find any missing angles or missing sides. And just keep in mind that when you're looking for an angle measure, be sure to use the inverse trig function or the arc trig function to do so. Let's try another law of sines practice problem. In triangle ABC, angle B is equal to 115 degrees, side B is 23.8, and side C is 45.6. Let's solve the triangle. Sketching this, I get something that looks like this. Now notice how I didn't actually draw a complete triangle. It's actually impossible to draw a triangle given this information, because look at the information here. If 115 degrees is the biggest angle of this triangle, because all three add up to 180, then the 23.8 has to be the longest side of the triangle. Remember that each opposite side length to each angle has to correspond with its actual angle measure. Opposite of angle C is 45.6, which means that angle C would have to be more than 115 degrees. If that were true, adding something more than 115 to something 115 degrees would be already more than 180. Just based on this logic, we can't actually draw a triangle given this information. Therefore, we can say that there's no solution given this information. Now let's just say that you didn't notice this and you tried to draw a triangle and use the law of sines. You went ahead and started by writing the law of sines, then you substituted in the information that you knew, you did some cross multiplication and rewrote the equation as 23.8 times sine of angle C is equal to sine of 115 degrees times 45.6. Then you divided both sides by 23.8 to write sine of angle C is equal to sine of 115 degrees times 45.6 all over 23.8. And finally, when you take the arc sine of the entire right side, you'll find out for angle C that you get an undefined message in the calculator. So if you happen to not see that you can't actually draw the triangle, you could absolutely use the law of sines, and if you get this undefined message, it means that you couldn't draw a triangle to begin with. Either way, when you're dealing with these triangles, keep a lookout when you're given the SSA information so that you're wary of these types of situations. Let's try one last law of sines problem here. In triangle ABC, angle B is 36 degrees, side B is equal to 5, and side C is equal to 8. Let's solve this triangle. If you'd like to, pause the video and try to sketch it on your own, and then you can see if we have the same type of sketch. Once again, we have this last case of this SSA where we could have the ambiguous case. Just to be sure, let's use our good old SOHCAHTOA with the height here and the right triangle to figure out what the height of this triangle is. Using our right triangle, we can say that sine of 36 degrees is equal to the height over 8, or opposite over hypotenuse. Multiplying both sides by 8, we can say that the height is equal to 8 times sine of 36 degrees. And plugging that into a calculator, the height is about 4.7. It's important to see here that the height is less than 5, since 5 is the hypotenuse of the triangle on the right. And since 5, which is the opposite side of our angle of 36 degrees, is shorter than the adjacent side of 8, we've now confirmed that we can actually draw two triangles given the information that we have. Well, I drew my initial sketch with the side 5 right over here, and there's something really stopping us from drawing that same side of 5 over here. Again, we were just told that angle B was 36 degrees, and side B was 5, and side C was 8. Since they don't really tell us where those sides have to be, then side 5 does have to be opposite of 36 degrees, but it could be in either one of these locations. In the rest of this example, I'm going to start by solving this triangle based on the way it's drawn now, and then I'll go ahead and do the same when our side length of 5 is in the other location. First, I wrote down my law of sines, then I substituted in the information that we know so that we can solve for angle C. Let's cross multiply and we'll get 5 times sine of C is equal to 8 times sine of 36. And dividing both sides by 5, we can say that sine of C is equal to 8 times sine of 36 over 5. And using arc sine or inverse sine of the right side, we can plug this into a calculator and find that C is equal to about 70.1 degrees. Now that we know that this angle right here is 70.1 degrees, we can use that along with the 36 degrees we already have, add them together, and subtract them from 180. In doing so, we find out this angle A here is going to be 73.9 degrees. Using this newfound information, let's write another proportion. We can write A over sine of 73.9 degrees is equal to 5 over sine of 36 degrees. Cross multiplying, we get the equation A times sine of 36 is equal to 5 times sine of 73.9. Dividing both sides by sine of 36, we get A equals 5 times sine of 73.9 over sine of 36. Plugging this into a calculator, we get that A is about 8.2. At this point, we have all 6 pieces of information for this original triangle. And just confirming that we have everything, we know angle A is 73.9 degrees, side A is 8.2, angle B is 36 degrees, and side B is 5, and angle C is 70.1 degrees, and side C is 8. Now let's consider the second case where the side length of 5 isn't drawn where it currently is. Let's take this side length of 5 and move it over here where it could also be located. Since it's looking a little messy, I just redrew it over here and took away some things. And what you want to notice here is that side of 5 is now actually going to be over here. In addition, this triangle right here is an isosceles triangle, which means this angle here also has to be 70.1 degrees. Since this angle right here makes a linear pair with the 70.1 degrees, we can take 180 degrees and subtract the 70.1 degrees to find out that that angle measure is going to be 109.9 degrees, or its supplement. Cleaning this up even more, here's another version of the triangle that we could draw, given our initial SS and A. Let's see what we have so far. We know angle B is 36 degrees because that was given in the beginning, and that side B is equal to 5. We were also given in the beginning that side C is equal to 8. We know angle A plus B plus C equals 180 degrees. So by substituting in the angles that we know and solving for angle A, we find that angle A is equal to 34.1 degrees, and we can write that right over here. And while we're at it, let's just also put this 109.9 degrees in here as well. At this point, we really only have one thing we have to find, and that's going to be side A. Using our law of sines, we can substitute information we do know, and write that 5 over sine of 36 is equal to A over sine of 34.1. By cross multiplying, we can rewrite the equation as A times sine of 36 degrees is equal to 5 times sine of 34.1 degrees. Dividing both sides by sine of 36 degrees, we get A is equal to 5 times sine of 34.1 over sine of 36. Plugging this into a calculator, we find out that A is approximately equal to 4.8, and we can write that right inside here as our last bit of information. The big key takeaway here is that when the height of this triangle is less than the side length that's opposite of the angle we're given, and that's less than the adjacent side of 8 in this problem, we're going to have 2 possible triangles. When you realize that that last side length that's opposite of the angle could hinge back and forth, you know that you can draw 2 triangles and you have to solve for both of them. Now that we've practiced using the law of sines, let's practice using the law of cosines. In triangle ABC, angle B is 125.2 degrees, side A is 32, and side C is 48. Let's solve the triangle. As usual, let's start by drawing a triangle. Here's a sketch of the triangle that I made, and it looks like the given information we have consists of SAS, or side angle side. Remember, when the given information you have is SAS, you're going to use the law of cosines instead of the law of sines. We don't know angle A yet, but we know that side A is equal to 32, so I'm going to fill that in here. We know angle B is 125.2 degrees, but we don't know side B. And finally, we're given that side C is equal to 48. Now let's go ahead and write down the law of cosines formulas. Here are the 3 different law of cosines formulas that we can choose from. While it may look a little bit overwhelming, try to remember that they're all just different versions of the same thing, depending on which angle you're working with. Since we have angle B here, it's important to note that we should use the law of cosines formula that has cosine of that angle. So let's start by just writing the law of cosines down, and substituting in the information that we're given, we're going to get b squared is equal to 32 squared plus 48 squared minus 2 times 32 times 48 times cosine of 125.2. 32 squared is 1024, 48 squared is 2304, and 2 times 32 times 48 is equal to 3072. Then multiplying this negative 3072 by cosine of 125.2, we get positive 1770.8. Combining everything together on the right side, we should get 5098.8, And taking the square root of both sides, we should find that b is approximately equal to 71.4, and we can write that right over here. Now that we have all three side lengths, as well as an angle with its corresponding side length, we can now use the law of sines to solve for the rest of the triangle. Using the law of sines, we can write the proportion 71.4 over sine of 125.2 is equal to 32 over sine of angle A. Cross multiplying, we can write the equation sine of A times 71.4 is equal to 32 times sine of 125.2. Dividing both sides by 71.4, we'll get sine of angle A is equal to 32 times sine of 125.2 all over 71.4. To solve for angle A, we need to use the inverse sine function to get rid of the sine function, and we'll have A is equal to arc sine or inverse sine of the entire right side. And putting this into a calculator, we find that angle A is about 21.48 degrees, which we can write right over here. That we have these two angles of 21.48 and 125.2, we can add them together to get 146.68. And subtracting that from 180 degrees, we find out that angle C is equal to 33.32 degrees. So just to recap real quick, since we were given the side angle and side of this triangle, we knew that we had to use the law of cosines to solve this triangle. By using the law of cosines, we were able to find out the side length of B was about 71.4. Then we just used the law of sines to solve the rest of the triangle. Once you've established the fact that you need to use the law of cosines, the next thing that's important is to notice which angle you're given, which is angle B here. Since we were told that angle B was 125.2 degrees, we should use the given law of cosines that has cosine of B in it. Besides that, it's just a bunch of plugging in algebra to solve for each of the values. And here's the final example of this video. Here we're going to solve one more law of cosines problem. In triangle ABC, side A is equal to 3.5, side B is equal to 4.7, and side C is equal to 2.8. Let's solve this triangle. If you'd like to go ahead and try it on your own, pause the video now, otherwise, let's do it together. Here's the triangle I drew, with all the given information labeled. Whenever you're given all three sides of a triangle, you can use the law of cosines to solve it. Keep in mind that it is possible that we can't draw a triangle if the side lengths aren't possible. The rule to check for that is if you add 2 of the side lengths, it has to be greater than the third side length. So 2.8 plus 3.5 is definitely bigger than 4.7, 3.5 plus 4.7 is bigger than 2.8, and 2.8 plus 4.7 is bigger than 3.5. Since all of this checks out, we can solve this triangle. Side A is 3.5, side B is 4.7, and side C is 2.8. When you're given all three sides of a triangle, it doesn't matter which formula you use for the law of cosines since we don't have any of the angle measures. Since it doesn't matter, I'm just going to choose the middle one here. Go ahead and write the formula, and then let's make some substitutions. Our A squared is going to be 3.5 squared, our C squared is 2.8 squared, and our A and C here are 3.5 and 2.8. And on the left side, our B squared is 4.7 squared. Evaluating this a bit, we get 4.7 squared is 22.09, 3.5 squared is 12.25, 2.8 squared is 7.84, and 2 times 3.5 times 2.8 is equal to 19.6. Subtracting this from both sides, the left side becomes this 2 over here, and dividing both sides by negative 19.6, we can say that cosine of B is equal to negative 2 over 19.6. To find this angle measure, we're going to have to use inverse cosine or arc cosine to find angle B. B is equal to arc cosine of negative 2 over 19.6, and plugging this into a calculator, we get that angle B is about 95.86 degrees. Now that we have a matching pair of an angle and its opposite side length, we can use the law of sines to solve the rest of this triangle. We can set up this proportion of 2.8 over sine of C is equal to 4.7 over sine of 95.86, and by cross multiplying, we can write the equation 4.7 times sine of C is equal to 2.8 times sine of 95.8. Dividing both sides by 4.7, we can write sine of C is equal to 2.8 times sine of 95.86 over 4.7. And just like earlier, to find angle C, we're going to have to use the arc sine or inverse sine function to do so. Angle C will equal arc sine of 2.8 times sine of 95.86 over 4.7. And plugging this into a calculator, we find that angle C is about 36.34 degrees. And finally, while you could use trig to find out angle A, let's just use some simple algebra to do so. Adding up angle B and angle C, we're going to get 132.2 degrees. And subtracting that from 180 degrees, we find out that angle A is going to be 47.8 degrees. And that's how you use the law of cosines and sines to solve a triangle when you're given all three sides. And that wraps up this video on solving some different practice problems using the law of sines and the law of cosines. Just remember to try to sketch your triangles and also identify what type of information that you're given from the start. The main types of information that you have to be careful of is when you're given the SSA, or the side, side, and angle. Other than that, it's just a lot of plugging in and solving for missing side lengths using a bunch of algebra. If you found this video helpful, please let me know in the comment section below or just give this video a thumbs up. As always, keep up the good work, and I'll see you in the next one.